Today we're going to look at the general case of projectile motion. And when I say the general case, we've already talked about projectile motion. There are no new concepts going on, but now we're not dealing with any simplifying assumptions. For example, we talked about zero launch height recently, where objects were fired from or thrown or whatever from ground height. That is no longer the case. We also talked about the simple case of zero launch angle, where the object was thrown horizontally from some height. That is also not the case. We're at some angle, so that initial height is not zero. The initial y component of the velocity is not zero. The velocity will, in general, have both x and y components. So this is the most general case, but there's nothing new happening conceptually. There are no new equations that we're adding that we can use. But there are a few key things to note. Number one, the symmetry that we talked about doesn't apply for the whole motion. The motion is symmetric up to the point where the object reaches its original height again, if it's fired upward at an angle. Objects could also be thrown downward at an angle, and then there wouldn't be symmetry at all. But for an object fired upward at an angle, there is symmetry for this first part of the motion, but then this last bit obviously has no corresponding piece of motion over on this side of things. So symmetry applies partially, but for most cases, if I say, if we're going from ground height, I could ask you, well, what happens if we double the initial speed? And you could work that out and get that, the distance it travels is 4 times the initial or whatever. But for general projectile motion, there isn't that straightforward relationship between variables a lot of the time. One other thing to note is that the range equation that we derived, delta x equals v naught squared sine 2 theta over g. Just want to remind you that this was for the case where we started at ground height. Therefore, it does not apply when we are referring to general projectile motion. We cannot use this, period. We'll be using our normal 5 kinematic equations, as always, plugging in only values that are x components or only values that are y components. Alright, so let's take a look at an example here. A child fires a rock from his slingshot, giving an initial velocity of 12 meters per second at 31 degrees above the horizontal. The rock was fired from 2.7 meters off the ground. Find the horizontal distance the rock travels in the air. We'll leave the other two to later. So when we want to find the horizontal distance the rock travels in the air, if we were dealing with the case of zero launch height, where our object winds up at the height it starts at, then we could use the range equation and be done straight away. But we cannot use the range equation for cases of general projectile motion. We have to go back to what we originally did with our first simple case, our horizontal, the case where our objects were thrown horizontally, where we use the time-dependent equation in the y direction to solve for time, and then plug that back in to the x equation to find the distance our object travels horizontally. So just as we did for zero launch angle, we would often say delta y equals minus 1/2 gt squared, but that was because we were applying the time-dependent equation in the y direction, and in that case, our initial velocity in the y direction was 0. Now it's not. So delta y, we start 2.7 meters off the ground, which means that if we call the ground height 0, we call our starting height 2.7, then our delta y would be y final minus y naught, 0 minus 2.7, so negative 2.7. The y component of our initial velocity means we need to break this initial velocity up into components. We've got 12 meters per second at 31 degrees above the horizontal. Think about those components. Okay, opposite is sine, so the y component of that velocity is 12 sine 31 times what we're looking for. And then the acceleration is 9.8 meters per second squared downward. And if we call that initial velocity positive, that's an upward. Well, the y component is upward. We need to call this downward acceleration negative times squared. And we can punch that into our calculator. We want to solve, get 0 on one side of our equation, so we move the 2.7 to the other side. And from there we can type it into the graph in our calculator. Half times 9.8 gets us 4.9 t squared. So into my graph I can type 2.7 plus 12 sine 31 times x minus 4.9 x squared. You can graph it and then find the time. Calc 0, left bound, right bound, guess, whatever. And we see that the time is 1.6, whatever. And then in order to find the horizontal distance our object travels, we're going to plug that into our time-dependent equation in the x direction. In the x direction, remember the acceleration is 0, so the time-dependent equation just becomes velocity times time. So that distance we want to find out is equal to the x component of the velocity, which would be 12 cosine 31 times time, which is that value we just found, which your calculator now automatically has stored as x. So multiply that by 12 cosine 31, and find that the horizontal distance this travels is 16.505, which with two sig figs would round to 17 meters. So for finding the distance an object travels in the air, again, to summarize, we use the time-dependent equation in the y direction to find time, plug that into the x equation to find our distance. So the next part of the question asks us what the maximum height is that the rock reaches. We've done this problem before. The only difference here is that now our initial height, our y naught, is not 0. Our y naught is 2.7 meters. So what do we know at maximum height? We know that the y component of our, not initial, the y component of the final velocity is going to be 0, because at maximum height in the vertical direction comes to rest for a moment. So then, given the variables that we know and what we don't know, the best way to work this one out is to plug our values into the time-independent equation. Again, if we're calling down negative, our acceleration is negative 9.8. Delta y, remember, is y final minus y naught. So maximum height in this case is going to be y final, and y naught, our initial y, is 2.7. And then in the y direction, the velocity at the max height is 0, and the initial is not just 12. Remember, always plug in components into our kinematic equations. And the y component of the initial velocity is 12 sine 31, just like it was up here. So then we do calculator stuff. 12 sine 31 squared divided by, there's a negative, so it's 0 minus that, but that negative cancels out with the negative on the 9.8. 2 times 9.8 is 19.6. So divide by 19.6. That's equal to y final minus 2.7 plus 2.7. You can see that the maximum height is 4.6488 whatever. With two sig figs, that rounds to be about 4.6 meters. All right. Velocity of the rock as it hits the ground. Again, this is something that we've done before. We did this problem when we were doing zero launch angle. As is always the case with projectile motion, the x component of the acceleration is 0, which means that the final velocity in the x direction is the same thing as the initial velocity in the x direction, which is just the x component of our initial velocity. 12 meters per second, 31 degrees, so that's 12 cosine 31. And in my calculator, I'm going to store that as x. Okay, now to find the y component of the velocity, we think about what variables we have, what we're trying to find out, and the time-independent equation is the one that we can use to immediately find the y component of the final velocity. Acceleration still negative 9.8. In this case, we're talking about going to the ground, so our delta y, negative 2.7, just like it was in part A. And that's equal to the final y component of the velocity squared minus initial, which is still 12 sine 31, as it was in the previous two parts. And then we're just doing algebra. 2 times 9.8 times 2.7, and then we add 12 sine 31 squared, take a square root, and we get the y component of our final velocity is 9.54 or something, which I will store in my calculator as y. And then, of course, once we have an x and a y component, to find the magnitude, we take the square root of the x component squared plus the y component squared, which comes out to about 2 sig figs 14 meters per second. And to find the angle, we take the inverse tangent of the y component over the x component. My calculator gives me 42.8, so about 43 degrees. Then we think about where it's going. Well, when it hits the ground, it's going to still be going forward, but it will also be heading downward. It's 43 degrees below the horizontal. So hopefully for all of these, you see that none of these questions are totally new. We've done things like this in our special cases problems. We're not applying any new concepts. We're just plugging stuff into our equations, following a lot of the same patterns that we have in the past.